Good morning, class. Today, I thought I would focus on one particular application of the material we've been studying, and this is the series Charging RL Circuit. I do have numerous other applications for the charging RC circuit, as well as for the discharging RL and RC circuits. But in the interest of simplicity, I just selected one of those topics. So what we have here, this is meant to be a switch. Here is the resistor, the inductor, and the battery. So I'd like to start with the first question. In my opinion, this is really the most interesting thing. Okay, it says, if the resistance, inductance, and voltage are constants, prove that the current in a series charging RL circuit is given by, we have current is equal to capital E over R, and then in brackets 1 minus the exponential function whose exponent is, and this is negative little t, so the negative of time, over, in the denominator here, this would be tau, your time constant, which is equal to L divided by R for this kind of circuit. At any time t after the switch is closed. Now this is a formula you would have been using right from the beginning of your program here. Although you've never seen where the formula comes from, and unbelievably, we can derive this formula now using the skills that you've learned in this first unit of the course. So all we need to do that is we're going to need to use Kirchhoff's voltage law for the circuit, and that's very simple, and you know that. And just one other little formula that we've been using in our math courses, and it's the formula for voltage across the inductor. It is equal to the inductance L multiplied by di by dt. So multiplied by the first derivative of current. And again, you started using that formula back in math 1331. So fall of your second year is when you were introduced to that formula. But anyway, let's go ahead and begin. Question 1. So what we have in our circuit is an inductor and a resistor connected in series to the battery. So here is what we know according to Kirchhoff's voltage law. We have the following. The voltage across the inductor plus the voltage across the resistor is equal to E at all times. Now again, for VL, we use this, L times di by dt. That's what we can use in place of the voltage across the inductor. Plus, for VR, we simply use Ohm's law. So this is I times R, okay, or R times I, since I is the variable. Okay, so I put the constant in front of the variable, like that. Okay, so now we would like to treat this as a first order linear differential equation, which is what we've been working on throughout this unit. And remember, in order to do that, we have to have this isolated in the first term right here, di. So how can I accomplish that here? Well, first I'm going to multiply all terms by the differential dt. Okay, so that looks pretty good. Lastly, all we have to do is divide all of the terms by L. And let's take a look at what we have. So you should be comparing this now to our general formula. So you'll remember the general formula looked like this. It had dy plus p times y dx is q dx. Okay, so clearly here we've changed our independent variable to t, and our dependent variable has changed from y to I. Okay, so that's very clear. But the other thing now that we can see when looking at our equation is that E over L, which is a constant, and by this language here, when they say that they are constants, it means they're just numeric, just numbers, right? Like maybe 20 volts, maybe 1 Henry, 2 ohms, right? Just numeric values. So that means that this will also be just a number, and this will also be just a number, and this is our Q, and right here, this is our P. Okay, so we know that P is equal to the number R divided by L. So this means we can work out our integrating factor, since it will be e to the integral of P dt. So it is e to the integral of R over L dt. Okay, so we just have to integrate this exponent. So if that's just a constant, just a number, then its integral with respect to t is this, R over L times t. Okay, because it's like taking R over L and multiplying it by the integral of the number 1 with respect to time. And the integral of the number 1, of course, is t. Okay, so this is our integrating factor. So I think you know that what we do next is we write out on the left side the integrating factor multiplied by that dependent variable. So in this case, there's the integrating factor, and we don't multiply it by y, we multiply it in this case by I, since that is the dependent variable. On the right side, you always begin with the integral sign, and then with q, so q in this case is the number E over L, multiplied by the integrating factor, which is this exponential function. And normally we would have dx here, so this is where we would have dt. Okay, maybe I'm gonna just grab that formula page really quickly. See, I was just following this part right here, but of course the difference is where it says dx, of course we're going to have dt, and where it says y, we're going to have I. So I just did this right here, integrating factor multiplied by I. On the right side, integral sign first, q, integrating factor dt. All right, so to continue, we need to actually integrate this function right here with respect to time. Well, it's an exponential function, and the derivative of the exponent is just a constant. So the derivative of this exponent would be R over L. And so that means the integral of this has E over L multiplied by, now the integral of this function. To integrate it, all you do is repeat the exponential function, but in front of that we would have 1 over r over L, since r over L is the derivative of the exponent. And then here, of course, plus a constant. So there's my constant at the end. Okay, let's simplify this. 1 over r over L is the same as L over r. So this now becomes E over R. And we are doing very well. We have left side and right side. And so you know that at this point in time, we always have solved for the constant of integration to calculate, or in order to rather find the particular solution. So if we can, we would now solve for that constant. And we certainly can for this kind of circuit, because we know that we start to measure time at the instant we close the switch. So at time 0, the current has not yet built up in the circuit. So at time 0, the current is 0. So that's the initial condition, and that's what we can use here. So we say at t equals 0, the current is equal to 0. And so that allows us to substitute 0 right here, 0 right here, and 0 right here. So let's see what that will give us. On the left side then, we'll have e to the 0 times 0. And on the right side, e over r times e to the 0 plus c. This, of course, is 0, but this is not. This is e over r times 1. So what does that mean? C is the negative of e over r. So that is what we substitute here. We're going to have now left side equals, we're going to write out this right-hand side, but with negative e over r in this spot. So let's do that. I'm going to just move the paper up to here. Wait, I'd like you to be able to still see this, and you can, so that's good. Slide this down. Okay, so we're going to write this as the left side here. Here's the right side. But where the plus c is, we now put minus e over r, like that. Okay, so how would we now be solving for the current? We would just be dividing all terms by that integrating factor. So let's go ahead and do that. We're going to take all the terms and divide them by the integrating factor. So I'll show it maybe in this step so that you don't get confused. Okay, so we're going to go like this and divide both of those terms by this exponential function here. Okay, so now when you take the first term and divide it by this exponential function, you're just going to get the constant e over r. Minus the second term here is e over r divided by the exponential function, but that's the same as e over r multiplied by the exponential function with a negative exponent, like that. Okay, so now we're very, very close to getting our result. Let's common factor e over r from both of the terms. Just like that. And lastly, if we want this to look like the formula we're accustomed to, all we have to do is use the fact that tau is L over R. And that means we can write this negative t divided by L over R. Just like that. Okay, and that's it. So I hope you found that example as interesting as I do. I think it's pretty remarkable that a formula that you've been working with since your very first semester at Niagara College can be derived by using the methods that you've finally learned in this differential equations course. So again, all we needed for that was Kirchhoff's voltage law, which you're pretty darn familiar with, and one formula that I introduced to you way back in Math 1331 for voltage across the inductor. Beyond that, all we did was follow the methods of solution based on the linear differential equation of the first order. Okay, so let's put that one aside. And as I said, I do have proofs for many other formulas for you, but in the interest of time, I'm not going to present them all on video. But if you're interested, I can also send you copies of the charging RC circuit as well as the discharging RL and RC circuits. Okay. Let's go on now and look at problem 3 on this sheet. So take a look. It says the resistance is 10 ohms, the voltage is 100 volts. The inductance varies with time according to L equals 5t plus 2. So this is the big difference in problem number 3. It is the fact that the inductance is not just a constant now, it's variable. Okay, but we're going to still use the methods that we used in the first example. So let's go ahead. I might as well start a new page. Let's go ahead and try this problem. Okay, so if you like, you can just begin the same way. So we got our VL, and we've got plus VR is equal to E. And then, you know, it's L times DI by DT. So in this example, L is 5t plus 2. Okay, so L times DI by DT plus this is I times R or R times I, and in problem 3 that's 10 times I, and the voltage in this question is 100. So we have this, but what do we want this to have? We want DI to be isolated. So we're going to multiply all terms by dt. We're also going to divide all terms by 5t plus 2. So let's go ahead and do that. Okay, so that is going to give us the following expression. There, now we're all set. So you should be able to compare that to our general formula for the linear differential equation. And you should be able to identify that P is equal to 10 divided by 5t plus 2. And here, of course, we would have our Q. So let's state the value of P. And let's go ahead and work out our integrating factor. Okay, so the integrating factor is of the form e to the integral of p dt, like this. So we need to correctly integrate that exponent now. And this might require you to use a u substitution. Okay, it kind of depends. Some of you might know the integral right away, but if not, I'm going to put a little star there. Let's come to the bottom of the page and solve that integral. So we have 10 over 5t plus 2 dt. So in performing the integral here, we let u equal the denominator. So u is 5t plus 2. This means du is 5 dt. So when we rewrite this, what do we have? We have u in the denominator, but what's in the numerator? Is it du? Well, it's 10 dt. It's not 5 dt. So it's double du. So we have 2 du over u, essentially. The 2 can be in front of the integral sign instead if you like, and the integral of du over u, as you know, is the ln of u. So we end up with 2 ln u here, which is 2 times the ln of 5t plus 2. So coming back up here, the exponent is 2 times the ln of 5t plus 2. So some of you may be able to look at that integral and correctly obtain this result, right? The denominator has an exponent only of 1, and in the numerator we do have a multiple of its derivative. The derivative of 5t plus 2 is 5. And we have a 10 here, which is where the 2 comes from. Okay, but if not, don't stress. You can just do this at the bottom of your page and successfully obtain this result. Now, you know that right away we take that coefficient of 2 and make it the exponent on 5t plus 2 so that our integrating factor is 5t plus 2 all squared, just like that. All right, so now we're at the point at which we write on the left side the integrating factor multiplied by the dependent variable I. Okay, so that corresponds to right here, integrating factor, dependent variable. Now we're going to do the right side. We're going to start with the integral sign. Then we're going to write q, and remember this is q, 100 over 5t plus 2. Now on that right side, it goes q times the integrating factor, and then dt. Okay, so it's normally q integrating factor dx, and of course for our application it's q integrating factor dt. So before performing this integration, clearly we're going to simplify this. This is the same as 100 times 5t plus 2. Okay, so we just reduce here. So, and it's up to you whether you keep the 100 after the integral sign or before the integral sign. It's kind of a matter of preference. Like that. And now to integrate this, you kind of have a choice. You can use a u substitution. And I say you have a choice, and that's because the exponent is 1. So we can use a u substitution, or we can bring in the 100 here, and then treat it like a polynomial, right? It'll be a binomial. So I think that I'm going to use a u substitution for this example. So I kind of took up a lot of space there. I'm going to do it just in the line above then here, okay? So I will just put this kind of a star, and I'm going to do it right here. So I have this to integrate. And all I'm going to do is I'm going to let u equal 5t plus 2. And that means du is 5 dt. Okay, so what are we integrating? This is u, so we're going to have a u over here. What else are we going to have? This is 100 dt, not 5 dt. So it is actually 20 times the du. So we end up with 20 u du. Okay. Oops. And now we just sort of ignore the 20, leave it as a constant multiplier. What's the integral of u to the 1? It's 1/2 u squared. So we end up with 20 times 1/2 u squared, or 10 u squared. And of course here we will have a plus c. So 10 times 5t plus 2 all squared plus c. And that's what goes here. 10 times 5t plus 2 all squared plus c. Okay, so that's just integrating this using a u substitution. And again, some of you might not have needed to write that all out. You could have just bumped this up from a 1 to a 2, remembering that you would then divide by 2 in the front. And 100 divided by 2 would get you to 50, but then you also have to remember to divide by 5, since 5 is the derivative of the inside of the bracket. So that's where the 10 comes in. But no worries, if you like to write it all out, that's cool. Okay, at this point in time, we would now work out the value of c. But I think I'll go to a new page because I don't have a terrible amount of room here. Okay, so I'm going to slide this up. Just want to keep it in your fields until we copy it down. So I'm going to slide that up to there. And I'm just going to write this out again. So 5t plus 2 all squared times I is 10 5t plus 2 all squared plus c. Okay, so that's where we left off. And now let's go ahead and solve for c. Using the same initial conditions, at time 0, the current is 0. So what does that do? The left side will be, I guess, 4 times 0. So basically 0. And on the right, though, we're putting a 0 here. So it's 10 times 2 squared, or 10 times 4, which is 40. And so that means the value of c is negative 40. Let's go back writing out this equation, but with negative 40 right in that spot. Just like that. Looks good. And then what would we do to solve for current? Because that's what our goal was in the problem, to determine the appropriate expression for current. So to solve for current, I'm going to be dividing both of these terms by 5t plus 2 all squared. So you can see that the first term then would just be 10, and in the second term we would have 40 over 5t plus 2 all squared, which would be the same as 40 times 5t plus 2 with an exponent of negative 2. However, I'm going to leave it just like this, since that's exactly what we were supposed to derive for problem 3. Okay? All right, so I'll do one more with you and I'll leave 2 problems for you. I think I'll do number 4 with you, okay? So, should I start it here? I don't know. Nah, let's go with another new page. Number 4. Okay, so let's read the question. So this time, what do we have? We have 300 volts for E, but look, a variable resistance and a variable inductance, and we've got our ultimate goal right here. So let us begin the problem. So we start with, VL plus VR is equal to E. So then it's L times di by dt. So L times di by dt. Okay, this term should be R times I. R times I, and over here is E. Okay, so that's looking pretty good. But before we begin to determine P, we have to multiply the terms by dt, all 3 of them, and divide all the terms by t squared plus 4. So let us go ahead and do that in our next step. Okay, so in this step, I did 2 things. I multiplied all of the terms by dt and divided all of the terms by t squared plus 4. And now it compares perfectly with this equation. Okay, so I can write the alternate form of this for you if I don't think I did yet, but the alternate form, of course, would look like this. So di plus I times P dt is Q dt. Okay, so this is like the right here. This guy is the general formula once we've changed y to I and x to t. Okay, so we can see that P is this right here. P is 4t over t squared plus 4. So that's excellent. And then we can go ahead and work out our integrating factor. So we want to integrate P now with respect to t for the exponent of the exponential function. So now it's up to you whether you need to do that down here. Okay, I will, I think, but it should just be 2 times the ln of t squared plus 4. Okay, because in the denominator, the exponent is a 1. What's the derivative of the denominator? 2t. What do we have here? 4t. So that's why this is 2 ln t squared plus 4. But if you want, you can do this for the integral. Call the denominator u. Okay, so if u is t squared plus 4, then du is 2t dt. This then becomes, okay, so u is in the bottom. Is this just du? No, it's 2 du. So we have 2 times du over u. So that's where we end up with 2 ln u, or 2 ln t squared plus 4. Okay? In simplifying here, the 2 becomes the exponent, and then we would cancel, and so we end up with t squared plus 4 all squared. But I can do it in steps. Okay, so 2 is now the exponent there, and then the integrating factor is t squared plus 4 all squared. All right, so if you want, I can even write this equation replacing x and y, and it would look like this, okay? So p dt, and an I, q, e, p dt, and a dt. So that is what we're going to use now. All right, and it is just this, but with the variables x and y replaced as required. Okay, so left side is integrating factor multiplied by I. Right side, integral sign first, then q, here's q, 300 over t squared plus 4, multiplied by the integrating factor, and a dt. So before attempting to integrate this expression, we have to reduce it. So simplify it first, and now we have t squared plus 4 to the 1. In order to integrate that, we might have considered using a u, right? A u substitution, because that's what we did in problem 3. But the difference here is, if I call this u, right? If u is t squared plus 4, then du would be 2t dt. 2t dt. That's hard to say, by the way. Well, for me anyway. Okay, 2 times t, right, would be the derivative in here. And there is no t out here. So a u substitution actually would not work, because 300 dt could never be a multiple of 2t dt. So a u substitution won't work. But luckily we have another option. Since this is just a 1, we can just, you know, treat this as though it's the integral of 300t squared plus 1200, a binomial, and just integrate each term separately. So what happens here? This becomes 1/3 times t cubed. And 300 times 1/3 t cubed is 100 t cubed. And what's the integral of 1200? It's just a constant, so its integral is 1200 times t. And then here we would have a plus c. Okay, so we can just go ahead and do it like that. Now, at this point, I might want to look at what the final answer is supposed to look like. And you see how 100t is factored here in the numerator? So that might mean that, you know, it would be nice to right away factor 100t here. Or we could why don't we first just solve for the constant? So solving for the constant is the same. At time 0, the current is 0. So that means the left side, is 4 squared times 0. What's the right side? If the 0's here and a 0's here, the right side is 0 plus c, right? So we get right away the fact that the constant is 0. And so you can see where this is going. We put a 0 here, then we'll common factor that binomial. Okay, so let me just slide that up. We're very, very close now. Okay, so I'm gonna write out, we're right there. I'm gonna write out the left side and have it equal to this, but with a 0 here. Right, and it would be plus 0 if you like. And then let's common factor, since we know what the answer looks like. So that's t squared plus 12 in here, isn't it? Yeah, I think so. And then solve for current. So dividing the right-hand side by that integrating factor gives us this expression for current. And if you take a look, you'll see that it perfectly matches the one on the handout. Okay, so honestly, I think that this is pretty fascinating. I'm kind of excited to be teaching this topic to you today. I do especially love that first question, which is a proof. It's not really the kind of question that I can put on your test, given that you are having a completely open book test, right? So it'd be kind of silly of me to ask you to just recopy this out. But I hope you found it as interesting as I did. And please go ahead. So the questions that I did not do with you today are 2 and 5. I'd love for you guys to try those, okay? And I will post solutions so that if you do get stuck at any point, you'll have my solutions there to guide you. Okay, thanks so much. Have a great day.